In this lesson, you will learn how to solve quadratic equations with real coefficients that have complex solutions. It's also important to understand what method to use depending on the initial form of the equation. We will use this flowchart to help us identify the best method for solving the quadratic equation. Depending on if it's in standard form or vertex form, we can use this flowchart to determine the method for solving. Let's look at example number 1. We have negative 45 minus x squared equals 655. Here, if the b equals 0, then we will solve by undoing the operations using the square root principle. Notice in this problem we do not have a bx term, so that means our b equals a 0. We can undo the operations to get x by itself. We'll first start by adding 45 to both sides. We'll need to bring down negative x squared equals 700 because 655 plus 45 equals 700. Notice we cannot take the square root until that x squared is by itself, so we'll now need to divide by negative 1. We find that x squared equals negative 700. This is where we can take the square root of both sides in order to solve for x. When you take the square root, remember to keep your plus or minus sign. We now need to simplify the square root of negative 700. We'll need to do prime factorization. We also need to recall that I equals the square root of a negative. When we do prime factorization, you can also recall that I squared equals negative 1. That's how you can deal with that negative. Imagine factoring out an I squared. Because that equals negative 1, it will make the 700 become positive. We'll now use prime numbers to do our prime factorization. Dividing by 2, we get 2 goes into 700 350 times. Dividing by another 2, 2 goes into 350 175 times. We'll now need to divide by 5. 5 goes into 175 35 times. Dividing by another 5, 5 goes into 35 7 times. 7 is prime, so we can divide by 7 and we get to our 1. So our prime factorization for negative 700 is this I squared, 2 times 2, 5 times 5, and a 7. We now will look for pairs of like factors. We have a pair of i's because it's I squared. We have a pair of 2's and a pair of 5's. So each of those things get to come outside of the radical. The 7 will stay inside. So our x will equal the plus or minus 10I square root of 7. Remember to keep your plus or minus sign. Each pair of factors got to come outside the radical, and then the 7 had to stay inside. Now that x is by itself, we can write our solution in set notation. Negative 10I, the square root of 7, and positive 10I, the square root of 7. In set notation, our solutions are always least to greatest. Let's look at example number 2. We have negative 4x squared plus 97 equals negative 491. Again, notice the b value would be 0 in this equation. We do not have a bx term, so we're able just to undo the operations. So we'll begin doing that by subtracting 97 on both sides. We have negative 4x squared equals negative 588. We can then divide both sides by negative 4. So we find that x squared equals a positive 147. When we take the square root, remember to use your plus or minus sign. We notice that 147 is not a perfect square, so we will have to do again the prime factorization. Divide by prime numbers until you get to 1. 147 is divisible by 7. 7 goes into 141. 7 goes into 147 21 times. We can divide by another 7. It goes into 21 3 times. 3 is prime, and so when we divide by itself, we get the 1. So notice we have a pair of 7s and a 3 left over. So our solution when x equals the plus or minus 7 square root of 3. We do not need the I in this example because we are taking the square root of a positive value. So our solution for x will be negative 7 the square root of 3 and positive 7 the square root of 3. Let's look at example number 3. We have x minus 5 quantity squared plus 9 equals 0. This equation is actually in vertex form. You will always undo the operations when given a quadratic in vertex form. So we'll first start with subtracting the 9. We find x minus 5 quantity squared equals negative 9. We can now take the square root of both sides, once again remembering your plus or minus sign. Of course, recalling again that I equals the square root of a negative, and I squared equals negative 1. So we can do the prime factorization of negative 9. However, it is a perfect square, so you should know that one. But if we factor out an I squared, that takes care of the negative. When we divide 9 by 3, we get a 3. Divide by another 3, and we get the 1. So we have a pair of i's and a pair of 3's. So the square root of negative 9 would be 3i. Notice on the left-hand side, we still have x minus 5. So we have not finished solving for x. We actually need to write two equations. X minus 5 equals a positive 3i, and x minus 5 equals a negative 3i. We will solve each of these equations by undoing the operation. So we're going to add 5 to both sides of the first equation. Recall, complex numbers are in the form of a plus bi. So we will write our solution as 5 minus 3i. Notice we cannot combine these because they're not like terms. Let's add 5 to the other equation on both sides. We get x equals 5 plus 3i. So our solutions for this equation will be 5 minus 3i and 5 plus 3i. Let's look at example number 4. Here we have 2x plus 5x squared minus 8. We first notice that our b value is not equal to 0. We do have a bx term. We then would determine if the equation is factorable. You could attempt factoring this equation, but many times it's easiest if you just solve for the discriminant and then you can determine if it's factorable. So let's go ahead and start by using the quadratic formula. We will need to move all the terms to one side and get the equation in standard form set equal to 0. So let's solve by adding 8 to both sides and put this in standard form. 5x squared plus 2x plus 8 equals 0. We can now name our a, b, and c in order to use the quadratic formula. Here our a equals 5, b equals 2, and c equals 8. Let's find the value of the discriminant first. So b squared minus 4ac, carefully plugging in each number where it belongs. So b is 2. We're going to square that. Then minus 4 times our a, which is 5, times our 8. That was our c value. We can calculate that using order of operation, and we find that our discriminant is a negative 156. So if you recall, a negative discriminant will tell us that we have two non-real solutions. Here's a great time to make a note that if you get a positive discriminant that is a perfect square, that means the quadratic is factorable. Also, if you get a discriminant that equals 0, the quadratic will be factorable. But because we have a negative discriminant, we will need to continue with the quadratic formula. Let's substitute in the quadratic formula our negative b, so negative 1 times our b value, plus or minus, we've already evaluated the b squared minus 4ac, so plugging in that negative 156, all over 2 times our a. Let's simplify each part, so negative 1 times 2, plus or minus, we'll handle that square root of the negative here in just a moment. Let's go ahead and simplify 2 times 5, which of course is 10. So taking the square root of negative 156, we need to do our prime factorization. Let's first factor out the I squared so we can take care of that negative. So 156 is divisible by 2. We get 78. We're again going to divide by 2. We get 39. Now we'll need to find a new prime because it's no longer divisible by 2. We can now divide by 3. We get 13. And then 13 is prime, so we will divide by itself and get our 1. So look for your pairs of like factors. Remember, you have the pair of i's, so we have I squared, which is a pair. We have a pair of 2's, so those things get to come outside of the radical, a 2 and an I. The 3 and the 13 will remain inside the radical, and you'll multiply them back together. So we have 2i, the square root of 39. At this step, notice that we can reduce the negative 2, the 2 in front of the I, square root of 39, and the 10 can all be divisible by 2. So we get negative 1 plus or minus 1i, the square root of 39, over 5. So that is our answer in simplest forms, so we can write our solution in set notation, least to greatest. So put the subtraction first and then the addition. So we get negative 1 minus I, the square root of 39, over 5, and negative 1 plus I, square root of 39, over 5 for our two solutions. Let's look at example number 5. Here we have negative 45 minus x squared equals 655. We're going to again use the quadratic formula on this equation. So let's set everything equal to 0. It is my preference to keep a positive, but it really would not matter. I'm going to add 45 and add the x squared in order to get 0 equals x squared plus 700. Remembering to put everything in the correct order, so your ax squared, bx, and your c. Notice this problem actually does not have a b term. So when we name our a, b, and c, a equals 1, b equals 0, and c equals 700. Let's evaluate the discriminant first. So b squared minus 4ac will have 0 squared minus 4 times 1 times 700. When you evaluate that value, we find that the discriminant equals a negative 2,800. Because that is negative, we will have two non-real solutions. So let's go ahead and use the quadratic formula in order to solve. So negative b plus or minus the square root, plugging in the value for that discriminant, negative 2,800, all over 2 times the a. Simplify each part so we get negative 1 times 0. We'll deal with that square root here in just a moment, and 2 times 1. So simplify each part. We get 0 plus or minus. We will simplify our radical all over 2. So let's do the prime factorization of negative 2,800. Let's first divide by I squared to take care of the negative. We get a positive 2,800. And then we'll divide by 2, actually several times, because when we divide by 2, we just continue to get even numbers for quite some time. So we're dividing by 2 with our prime factorization. We get here at 175. That is no longer divisible by 2. We now have to divide by 5. 5 goes into 175 35 times. 5 goes into 35 7 times. And then, of course, 7 is prime, so we'll divide by itself to get our 1. So we see our pairs. We have a pair of i's, 1, 2 pairs of 2's, and a pair of 5's. So we will multiply all those things together to get what comes outside of the radical. So 5 times 2 is 10. 10 times 2 is 20, and then we have our I. So we get 20i, the square root of 7. Well, notice we're supposed to take 0 and add and subtract. However, that would not change that value of the numerator. So we just have a positive negative 20i, the square root of 7, divided by 2. We can divide by that 2 to get our solution, plus or minus 10i, the square root of 7. So see that our solution is negative 10i, the square root of 7, and positive 10i, the square root of 7. Notice we have previously solved this example and got the same solution. So it will not matter what method you use. We could have undone the operations to solve as we did previously, or the quadratic formula in this case. Let's look at example number 6. Here we have negative 4x squared plus 97 equals negative 491. Again, let's use the quadratic equation. We're going to move all the terms to one side to get it set equal to 0. In this case, I'll leave the a as a negative, although it is my preference to have it as a positive. So we have negative 4x squared plus 588 equals 0. We'll name our a, b, and c values. So we have a equals negative 4, b equals 0, and c equals 588. Let's evaluate the discriminant. So b squared minus 4ac, plugging in 0 squared minus 4 times negative 4 times 588. When we found that value, it's 9,408. So if you'll recall, if that discriminant is positive, we will have two real solutions. This value is not a perfect square, so it's not factorable. If the discriminant was a perfect square, we would have gone back and been able to factor the quadratic equation. However, it is best to continue with this method or choose a different method from the start because our discriminant is not a perfect square, we will have a value that has a simplified radical. So let's continue with this method of quadratic formula. We have -1 times 0 plus or minus the square root of our discriminant, so that 9,408, all over 2 times -4. Let's simplify each part. So we get 0 plus or minus. We will simplify our radical all over -8. So let's do the prime factors of 9,408. We have quite a few 2's, so we're dividing by 2 for quite some time. When we get here, 2 goes into 294 and gives us 147. That's when we can no longer divide by 2. So there's 1, 2, 3, 4, 5, 6 2's that you can divide by before you have to choose a new prime number. 147 is divisible by 3. We get 49, and 49 is divisible by 7. We get a 7, and we will divide by itself to get 1. So quite a list of prime factors. We have 1, 2, 3, 4, 5, 6 2's, a 3, and 2 7's. So find your pairs of like factors. We have 1, 2, 3 pairs of 2's and a pair of 7's. So each pair gets to come out as that value. So 2 times 2 is 4, times 2 is 8, times 7 gives us 56. Of course, the 3 did not have a pair, so it has to stay inside the radical. Notice we're at the step where we add or subtract. Well, when you add or subtract 0, it will not change that solution. So we'll take 56 and divide it by -8. You can also consider the -56 divided by 8 will still have a positive and negative 7, because 56 divided by 8 is 7, the square root of 3. So our two solutions are -7 the square root of 3 and +7 the square root of 3. Notice these are the same solutions we previously found in our example when we worked this same problem. So solving quadratic equations, it's important that you understand what method to use based on how the problem is starting. Also use this flowchart to help you identify that method